Okay, we continue with the multi-degree of freedom systems and the eigenvalue problem. The procedure is similar to the system with 2 degree of freedoms, but here we deal with more than 2 equations. So definitely, again, we can write it in the form of the matrix and vectors, as you can see here. For example, for a system, for an undamped system, the free vibration equation can be something like this with a matrix M and matrix K, which matrix M is the mass matrix. It will be a n by n matrix, and n is the number of the degree of freedom or the number of the equations, and K is again an n by n matrix. X is a vector with n components, and we need to extract the characteristic equation or the frequency equation to obtain the frequency and mode shapes. The procedure is similar to the 2 degree of freedom system, as I told you. So for this purpose, we can consider the solution in the form of xi times by t, which is this xi is the amplitude of the response, and tt, which is a function of time, is the time part of your response. According to this solution that we assumed, we can see that the response for all of the degree of freedoms, or x1 to xn, will have the same time part. So we will vibrate synchronous with the same time with the same frequency, but the amplitudes are different. This is exactly the same assumption that we used in the 2 degree of freedom system. So we need to obtain the relation between the amplitudes for different responses for x1 to xn, which we call them the mode shapes. And similar to the 2 degree of freedom systems, we need first to obtain the natural frequencies, and then we will find a corresponding mode shapes for each frequency. So here, as I told you, the solution means that all of the coordinates x1 to xn will have synchronous motion, or they will vibrate synchronously, and the amplitude ratio of the coordinates are different, and we can obtain them by using the mode shapes. So for this purpose, we can substitute into the equation and consider the response t as a function of cosine or in the harmonic form. So by substituting t in the response in the equation of motion in the matrix form, for the non-trivial solution, the determinant of the matrix of coefficient again must be equal to 0. As you see, this is exactly the same equation that we extracted for the 2 degree of freedom systems, but this time this is an n by n equation. In 2 degree of freedom system, it was 2 by 2 equations. All of the matrices were 2 by 2, but here the matrices are n by n. So here we will have an equation from order 2 times by n, and we can extract n natural frequencies and n mode shapes similar to the 2 degree of freedom systems for a system with n degree of freedom as n degree of freedom systems. So we need to do the same, and from this equation, which is called the characteristic or frequency equation, we can obtain n natural frequencies, as you can see, omega 1 to omega n, and we can obtain n mode shapes corresponding to these natural frequencies. The most important frequency is always the lowest one, which is called omega 1, and this is also called the fundamental or first natural frequency. So usually in the practical problems, we seek for the first natural frequency because this is the most important one. And if we will have the resonance, usually the lower frequencies are more important, such as omega 1, because usually the system will be excited with the frequency of the first natural frequency, and it can cause the resonance phenomenon. Okay, we'll have one example to extract the equation of motion and the natural frequencies. Here we have a system, a very simple system with 3 degrees of freedoms, consists of three masses M1 to M3, three springs K1 to K3. We consider the generalized coordinates x1, as you can see, x2 and x3. And also this system is subjected to the external force F1, F2 and Ft, which they are applied to the mass M1 to M3 respectively. To extract the mode shape and the natural frequencies, here we assume that K1 to K3 are equal to K and M1 to M3 are equal to M. So we can use different methods. You can use the Newton's second law because this is a simple system. You can easily, by using the Newton's second law, you can plot the free body diagram. For example, for the mass M1, here we will have the mass M1, which is subjected to the motion and coordinates x1. If this mass m1 going to the positive direction of x1, we will have one force due to the k1, and it's equal to k1 times by x1. We will have another force due to the spring k2, and it's equal to k2 multiplied by x1 minus x2, because both edges of this spring, as you can see, are moving. So according to the direction of this force, the amplitude of the force is equal to k2 times by x1 minus x2. And also we have one external force in the right direction, which is called F1. We have the weight which is in vertical direction, so it do not appear in the equation of motion in the horizontal direction. If you write the force equation in horizontal direction, it will cause the acceleration x1 double dot in horizontal direction, and we will have F1 minus K1 x1 minus K2 times by x1 minus x2. It must be equal to m1 x1 double dot. Now you can simplify this and extract the first equation. For the second mass and third mass, you can write the same procedure. You can plot the free body diagram and obtain the equation of motion for the other masses. But also we can use the energy methods or Lagrange methods to extract the equation of motion. For this purpose, we need to write the kinetic energy. As you see, we will have three masses. So the kinetic energy will include three terms. The first term is the half times by mass m1 multiplied by its velocity, which is x1 dot squared, this term. The second mass is half times by mass m2 multiplied by its velocity, which is x2 dot squared. And finally, the kinetic energy due to this mass m3, which is half times by m3 x3 dot squared. Also, we will have the potential energy. This system, because the masses will remain in the same level of the vertical position, so there is no potential gravitational potential energy in V, and only we will have the potential energy which is stored in the springs. The first one is the potential energy is stored in this spring K1, and it's equal to half times by K1 times by its displacement, which is x1 squared, because it has only one movable edge, this term. The second term is due to the spring K2. Both edges of this spring are moving, so we will have half K2 times by x1 minus x2 squared, or x2 minus x1 squared. And finally, the last spring K3, which again the potential energy in this spring is equal to half K3 times by x2 minus x3 squared, or x3 minus x2 squared, no different. All of them will give you the same result. So now we have T and V. We have the equation of motion by using the Lagrange equation for each mass. You can easily write, and also you know that Q1 is F1, Q2 is F2, and finally Q3 is F3. So you can easily extract the equation of motion. But to obtain the natural frequency and mode shapes, we need to consider the free vibration response of the system, or we need to consider that the external forces are zero. I mean F1, F2, and F3, all of them are zero. So we will deal with an equation, matrix M multiplied by X double dot plus matrix K multiplied by X is equal to 0. And you know that this X is a vector with 3 components, and it's equal to x1, x2, and x3. So this is the vector x. So x double dot is x1 double dot, x2 double dot, and x3 double dot. Now we need to solve this equation with these two matrices, M and K. You can substitute for M1 to M3 and K1 to K3 from the problem description, M and K respectively, and then we can form the equation, the frequency equation or characteristic equation to obtain the natural frequencies. For this purpose, you can write the matrix of coefficients K minus M omega squared, and now we need to obtain the determinant of this matrix. If you write the determinant of this matrix, which is this component multiplied by the determinant of this, the small matrix, this component multiplied by the determinant of this matrix, and finally this component, which is 0, multiplied by the determinant of this matrix. So you can substitute and calculate the determinant of the matrix of the coefficient, and you can extract an equation from order 6, as you can see here. As I told you, when the system is with n degree of freedom, the characteristic equation will be an equation from order 2 times by n. Here we deal with a system with 3 degree of freedom, so the order of the algebraic equation or the characteristic equation is 2 times by 3, which is 6. Now we can substitute omega 2 with this value, k divided by m times by alpha. We use this relation only to simplify the equation of motion. And now if you substitute instead of omega squared k divided by m times by alpha, we can extract this equation from order 3 minus k cubed multiplied by alpha cubed. This is an algebraic equation from order 3. To obtain the roots of this equation, I think I have uploaded already the formula to obtain the roots for an algebraic equation from order 3. So you can use that root, that formula, or that algorithm to obtain the roots of this type of equations, or you can use your calculators to obtain the roots of these equations. We will have 3 roots for this equation, alpha 1, alpha 2, and alpha 3. By solving this equation, of course, before that, you can divide this equation by k cubed. As you can see, if you divided it by k cubed, you can extract an equation in terms of alpha. And now you can obtain these three roots for this equation. We will have alpha 1, alpha 2, and alpha 3, and from this definition, omega squared is equal to k alpha divided by m. We can obtain omega 1 to omega 3, or three different frequencies for this system, and they are omega 1, omega 2, and omega 3. So here, instead of alpha, you can substitute the numerical value of the roots, and then you can calculate that omega is a square root of k alpha divided by m. So this is three roots, and now we need to obtain the three mode shapes for this system. And for this purpose, we can substitute omega in this equation. In fact, in this matrix, because we have a matrix of similar to the 2-degree of freedom system, we will have a matrix K minus matrix M multiplied by omega squared. This matrix is multiplied by a vector x1, x2, and x3, and they must be equal to 0, as you know. So we will have three equations with three unknowns, x1, x2, and x3, which they are the amplitude of the response. Now we can substitute omega is equal to omega 1 to obtain the first mode shape. Then we can substitute omega is equal to omega 2 for the second mode shape. And finally, omega is equal to omega 3 to obtain the third mode shape. But here, as you know, because we deal with an eigenvalue problem, when you substitute omega is equal to omega 1, and omega 1 is the eigenvalue of this system, instead of three equations, we will have two equations with two unknowns. So by solving this system of the two equations with three unknowns, so by solving this system of algebraic equations, we can obtain only a relation between x1, x2, and x3, similar to the 2DOF systems. So here, if you substitute omega is equal to omega 1, we can extract the first mode shape and the relation between x1 to x3. As you can see, when you substitute omega is equal to omega 1, we will have this term, this component 2 minus 0.198 minus 1 and 0. This is the first equation. It means that this component, this component multiplied by x1 plus this component multiplied by x2 plus this component multiplied by x3, it's equal to 0. This is the first equation, this equation. The second equation can be obtained from this component multiplied by x1, this component multiplied by x2, and finally this component, which is minus 1, multiplied by x3. This is, it must be equal to 0 again. As you can see, the right hand side of all of the equations are 0. So this is the second equation. And finally, the third equation, which is this component multiplied by x1, this component multiplied by x2, and this component multiplied by x3, again must be equal to 0, which results in the third equation, as you see. So we have three equations with three unknowns, x1, x2, x1, x2, and x3, and finally x2 and x3. In fact, by solving this system of equations, you only can extract the relation between x1, x2, and x3. I mean, if you obtain, for example, here, from this equation, you will see that x2 is equal to 1.802 multiplied by x1. And from the third equation, you can obtain that x3 or x2 is equal to 0.802 times by x3. So if you substitute in the second equation for x1, substitute that x2 divided by 1.802, and instead of x3, you substitute x2 divided by 0.802, and simplify this, you will see that the second equation is equal to 0, and you will not have another extra equation. So only you can obtain a relation between x1, x2, and x3, as you can see. For example, from the first equation, you can write x2 as a function of x1. From the third equation, you can obtain that x3 is a function of x2, and it's equal to 1 divided by 0.802 times by x2. And also we know that from the first term, we know that the x2 is a function of x1, so we can write x3 as a function of x1, and it's equal to 1.802 divided by 0.802 times by x1. So you can see we find x2 and x3 as a function of x1, and this is the first mode shape. As you can see, the first mode shape is a function of x1 that we can substitute for x1 is equal to 1. So the first component is 1. The second component is 1.802 times by x1, which x1 is substitute 1. And finally, the last one, which is 2.246 multiplied by x1, which is substitute 1. So this is the first mode shape that you can extract from the first natural frequency. The second natural frequency can be obtained from this, the second mode shape can be obtained from the second natural frequency, and for the third one, you can substitute omega is equal to omega 3 and extract the relation between x1 to x3. So we will have three mode shapes with three natural frequencies as the response for an undamped system and free vibration. So now we want to obtain the free vibration of undamped system. For this purpose, as you see, we can extract this which is called mode shape, and also we can obtain the omega I, which is the frequency. For example, in the previous example, we had a system with 3 degrees of freedom, and so we extracted 3 natural frequencies. So this xt is equal to the x1, which is the first mode shape, multiplied by a1 times by cosine omega 1t plus v1. This is the response for the first frequency. x2, which is the second mode shape, multiplied by a2 times by cosine omega 2t plus v, and so of course this is v1 and this one is v2, the angle phase, and so on. This can be continued for n degree of freedoms. So this is the response of a system of an undamped system, and in fact this is the transient or free vibration response of this system. Now we can obtain the AI and Phi, which are called the constants for this response, can be obtained from the initial condition of your system. We need, for example, for a system with n degree of freedom, we need 2 times by n initial conditions. As you know, similar to the 2 degree of freedoms, we need 4 initial conditions, but here for a system with n degree of freedoms, we need 2 times by n initial conditions to obtain AI and Phi, which are the constants in this response. And also this mode shapes or modal vector and omega I, which are obtained in the previous procedure from the characteristic equation or frequency equation, and you can obtain them. Okay, so these are, of course, also they are called the eigenvalue and eigenvector for the response. Okay, any questions so far? Okay. Okay, for this week, we continue with the multi-degree of freedom systems. We will study the orthogonality of normal modes. You will see that what does it mean and what's the application of the orthogonality of the normal modes in the multi-degree of freedom systems. We will study the force vibration of undamped systems using the modal analysis, and finally the force vibration of viscosely damped systems. And you will see we will have different procedure for this type of systems. So first of all, we start with the orthogonality of normal modes. From the free vibration of an undamped system, when we consider the response similar to the previous slides, you saw that we consider the response as x times by a harmonic such as cosine omega t plus v, and then we substitute in the equation of motion, which was matrix M. We had the matrix M multiplied by x double dot plus matrix K multiplied by x. It was equal to 0 because this is a free vibration. So from here, if you substitute the x as a harmonic function such as cosine omega t and substitute here, you know that x double dot is equal to minus omega squared times by x. So if you substitute here and simplify this equation, you can extract this relation, which omega I in fact is the I's natural frequency of the system, and xi is the I's mode shape of the system. So this relation is or this equation will be satisfied because of our initial assumption, and we use this relation to obtain the free vibration response of the system. Now we will use a new characteristic of the modal vectors or mode shapes. We can, of course, here we will not discuss this, but it's possible if you refer to the reference books, it can be proved that the mode shapes are orthogonal with respect to the both mass and stiffness matrices. And what does it mean? Here you can see the definition of the orthogonal vectors. When we have orthogonal vectors, it means that this vector transpose multiplied by the matrix M, because we know that this vector is orthogonal with respect to this matrix M. So the vector transpose multiplied by matrix M multiplied by the orthogonal vector, it must be equal to 0 when I is not equal to j, and it must be equal to the diagonal component when I is equal to j. Or in other words, we can write it in the form of the matrix, and here you can see the matrix form, because the vectors of mode shapes are orthogonal with respect to M and K. We can form a new matrix which is called modal matrix. This matrix, modal matrix, of course this is the transpose of the modal matrix, or this is the modal matrix. And modal matrix is formed from the mode shapes. As you can see, the first column of the modal matrix is the first mode shape, the second column of the modal matrix is the second mode shape, and finally the nth column or the last column of the modal matrix is the last mode shape or the nth mode shape. So if you form this matrix, and if you form this equation, the modal matrix transpose multiplied by matrix M or matrix K in the second equation multiplied by the modal matrix, it must be equal to a diagonal matrix. As you can see, M11, M22, and the other components of this matrix are 0, as you can see. So I think you can guess that what is the application of this modal matrix. As you can see, I mean, when we have a system of n equation of motion, we have m times by x double dot plus k times by x, it's equal to 0, which is a system with n ordinary differential equations, which all of them are coupled because m and k, they are not diagonal. But you can see we can find a diagonal form for the matrix M by using the modal matrix, and also we find a diagonal form for the stiffness matrix by using the modal matrix. So we can convert this system by using this characteristic, and by using the modal matrix we can convert it into a new form of the equation of motion, which instead of n coupled ordinary differential equations, we will have n independent and separated ordinary differential equations, and easily we can solve them. For example, the first equation is m11 multiplied by x1 double dot plus k11 multiplied by x1, and it's equal to some terms here in the right hand side. So this is the characteristic, because the first matrix, the mass matrix, the first component is m11 and other component is 0. So this component multiplied by x2 is 0, again is 0, and the last one is 0. So in the first equation we only have x1 double dot, and also the stiffness matrix, again the first component is k11 and other components are 0. So it means that we only have the x1 in the first equation. So this is an equation from order 2, or an ordinary differential equation from order 2, and which is independent, and this only we have one unknown, which is x1, and by solving this equation independently you can obtain the x1. From the second equation can be obtained, x2 can be obtained. From the third one you can obtain x3, and finally from the nth one you can obtain the xn. So you can obtain all of the responses or all of the coordinates by using the modal matrix characteristic, and you can obtain an independent ordinary differential equation and solve them separately to obtain the response. But how to do this procedure? We can obtain first these matrices. As I told you, you need to obtain these matrices. For this purpose, we first normalize the modal vectors x such that the matrix M is equal to 1. So from here, you can obtain that Kii, I mean K1, K2 to Knn are equal to omega 1 squared, omega 2 squared to omega n squared. From here, you can obtain the amplitude, because you know that these vectors are functions of, for example, x1. For example, in the system with 3 degrees of freedoms, in previous example, we find that the mode shapes was, for example, 1, I don't know, some other numbers like 0.2, or for example, 0.4 multiplied by x1. This is the first mode shape. So this x1 must be obtained when you substitute this modal vector in the modal matrix. We have one unknown, which is x1, and this x1 will obtain from this equation by normalizing the modal vectors x. And you will see in the examples that what is the procedure is pretty simple and it's not very complicated, and you can easily obtain this matrix x, and also you can obtain the matrix, new matrix for the stiffness and the mass. Okay, for the force vibration, we can continue on Wednesday. If you don't have any question, we can wrap up this session. Any question or any issue regarding to these topics. Any question? For the short test, as I told you, the topics are those which were covered during the week 5 to week 11, sorry. So we will have the force vibration of single degree of freedom system subjected to the non-periodic and non-harmonic excitation. I mean, you need to know the Laplace convolution integral and the, I think, the impulse function. And also we will have the 2 degree of freedom system. Of course, only the free vibration or force vibration of the 2 degree of freedom system. And this chapter, which is multi-degree of freedom, will not be considered in the shortest two. I guess it will be on evening. I will check it with you, and anytime which you are free, you can do your final, your short test. Okay. Any other question? Okay. Thank you for your attention, and we continue on Wednesday. Thank you.